Hello and welcome back. In our previous video, we discussed naming simple substituents on alkane parent chains that were comprised just of a straight chain alkyl group, such as with one carbon, we'd have a methyl group. With two carbons, we'd have a ethyl group, and so on. So, for example, if we had a chain that had, say, a parent chain that had, say, 5 carbons on it, and at the third carbon we had maybe a 2-carbon chain coming off, then this would be an ethyl group on the parent pentane chain. Okay, so we would name that as eth for 2 carbons plus yl to indicate that it's a substituent. Sometimes we can have substituents that aren't simple straight chain alkanes, and so for substituents that have branches on them, substituents, if you will, on those substituents, then those are called complex substituents. And those complex substituents can get fairly complicated. We're going to name just some simple ones. So we're going to look at the common way to name those, some of those, and the IUPAC way of naming these complex substituents. So the first thing we do when naming a complex substituent is identify the longest carbon chain within that substituent, which we've done here. So let's kind of start over. So we have our parent chain here. So we have 11 carbons in the parent, that's undecane, and from the left side our substituent is at the 6th carbon. From the right side we have 1, 2, 3, 4, 5, again at the 6th carbon, so it doesn't matter if we go from left to right, we have a substituent at the 6th carbon. Okay, so that makes our longest carbon chain follow the blue path. So the carbon chain that's numbered along the red path, this is actually a substituent. So it's a complex substituent because it has this methyl group hanging off of the 4-carbon chain. So we have a 4-carbon chain in this substituent, 1, 2, 3, 4. So the substituent itself has a parent chain. And then it has a substituent hanging off of the substituent's parent chain, where it has, in this case, a methyl group. So this substituent, our substituent is outlined or highlighted in green here. Our substituent has a 4-carbon parent chain, and then it has a methyl group as a substituent on the substituent. Okay, so our parent on the substituent, our substituent's parent chain is butyl because it has 4 carbons. So we name it with a YL ending again. And then we name and number the substituent's side group, or the substituent's substituent, and that is a methyl. And that methyl group is at the 2nd carbon on that butyl chain. So let's say 2-methyl. Now numbering these is a little bit different from numbering a parent chain, because you have to start numbering at the carbon that is attached to the parent chain. So we have to start numbering at the carbon attached to the parent chain. That's going to be carbon number 1. So in this case, it's going to be, so this would be carbon number 1 attached to the parent. Carbon 2 has the substituent. Carbon 3 is next, and then carbon 4. So that's why the substituent is called 2-methyl-butyl. So this molecule would be 2-methyl-butyl undecane. So to make it easier, sometimes we just have common names for these substituents, and it's good to memorize most of these common names for the substituents because we're going to see them a lot. And I'll tell you the ones that we're going to see a lot in our class, so you'll be able to remember those. So these are called Brandt substituents or complex substituents, and again they have common names. So on the left, if we have a parent chain that has a 3-carbon straight chain attached to it, that 3-carbon chain is called a propyl group. If the parent is attached to a 3-carbon chain at the center instead of at the end, then that is called an isopropyl group. That's why the common name for the alcohol you buy at the store for cleansing, for disinfection, is called isopropyl alcohol, because the OH group on that alcohol molecule is attached at the second carbon. So that's called isopropyl. Now the IUPAC name for this substituent would be 1-methyl-ethyl. It's called 1-methyl-ethyl because attached to the parent we have a 2-carbon chain with a methyl group hanging off of that 2-carbon chain at the first carbon. So the carbon attached to the parent is numbered 1, the second carbon is numbered 2, and we have a methyl group attached at the first carbon. So it is called 1-methyl-ethyl. So for example, let's say, I'm going to draw a long chain here. So this is a 1, 2, 3, 4, 5, 6, 7, 8 carbon chain. So let's say at carbon number 4, I attach this isopropyl group. Okay, so now let's number that isopropyl group. This would be carbon number 1, this would be carbon number 2 as a complex substituent, giving it an IUPAC name, and at the first carbon on the substituent we have a methyl group. So this would be 1-methyl-ethyl. Okay, 1-methyl-ethyl, and we put that in parentheses because it's a complex substituent, 1-methyl-ethyl octane in this case. Or we could also call this isopropyl octane. So for a propyl substituent, we have 2 possibilities. We could have it attached at the end, as in this case on the left, or we could have the parent attached at the middle for the case on the right, which would be an isopropyl group. Now there are 4 different possibilities for a 4-carbon substituent. And so the one on the left is a straight chain butyl group where it's a straight chain with the first carbon attached to the parent and then all the other carbons follow in a line. Also, if we have a 4-carbon substituent as we have in this box, it's either some branch substituents. We could have a sec butyl where that parent is attached now not at the first carbon of the 4-carbon chain, but at the second carbon of that chain. So that's why it's called sec butyl. It's attached to the second carbon. And the way to name this as a complex substituent would be 1-methylpropyl, because we have this one methyl group, at the I'm sorry, I numbered that thing wrong. So I was only pointing out that the parent was attached at the second carbon. I wasn't trying to say that was the correct way to number the substituent. So if we want to number the substituent to give it the IUPAC name, we have to start numbering at the carbon attached to the parent. And at that first carbon, we have a methyl group. So this would be a propyl chain because it has 3 carbons with a methyl group attached at the first carbon. So that would be a 1-methylpropyl substituent. Okay. The next one is called isobutyl because it's an isomer of a butyl group. So that's the common name for it. This one has a 3-carbon chain with a methyl group attached at the second carbon. So we start numbering for the complex substituent nomenclature at the carbon attached to the parent. So this would be a propyl group, and we have a methyl group at the second carbon. So you could call this substituent an isobutyl or a 2-methylpropyl substituent. The next substituent on the right, okay, has a carbon attached to the parent that has 3 methyl groups attached. So that is called a tert butyl, which is also short for tertiary butyl. And this also could be called T-butyl as another way to name it as a common name. And you'll often see T-butyl. That's the normal way of seeing this substituent. And this also could be named as a 1,1-dimethyl-ethyl group, because if we start numbering at the carbon attached to the parent, let's just number it this way. This would be an ethyl group that has two methyls attached. So this would be 1,1-dimethyl ethyl. But the most common way you'll see this named is going to be as a T-butyl or tert-butyl group. So these are all good to memorize, but the most important ones here are just going to be the straight chain butyl group and the tert-butyl. You'll see that tert-butyl group over and over in this course, so it's good to memorize it. For example, this is T-butyl alcohol. Alright, so again, the carbons in the parent chain have to be numbered to give a locant to the substituents, or a number to the substituents. So we want to give the lowest number to the first substituent. So if we have 2-methylpentane, that means there's a methyl group on carbon 2 of the pentane chain. If we have 3-methylpentane, that means there's a methyl group on carbon 3 of the pentane chain. So we can identify 2-methylpentane from 3-methylpentane as isomers of each other simply by naming them, and that will help us to identify that they are in fact isomers of each other. Now if I drew a molecule like this, you might think, well, there could be another option here. What if I put a methyl group over here? Is that 4-methylpentane? Oops, I didn't mean to include that one at the bottom there, sorry. Is that 4-methylpentane? Well, no, that's not. That's actually 2-methylpentane, because remember, I want to give my substituents the lowest number possible. I want to find my longest carbon chain and start numbering at the end that is closest to the first substituent. So I'm going to start over here on the right. 1, 2, 3, 4, 5. So this is again 2-methylpentane. So you can see that these two molecules on the left and right are actually the same. And the one in the center is an isomer of those. So again, we want to give our substituents the lowest number possible. That's like what we were just talking about. This would be 2-methylheptane on the left. And on the right, we have it numbered incorrectly because that has the methyl group at the 6th carbon. We want to make sure we put our methyl group, we want to give our methyl group the lowest number possible, but you have to start numbering from one end of the molecule, of the parent chain. So when we have multiple substituents, we want to give the lowest number to the first substituent, okay? So correct is on the left, where we have our methyl group at the 2nd carbon. On the right, it might seem like it would be correct to number from the right, because we would have 2 methyl groups at the 3rd position and 1 methyl group at the 6th, but that doesn't matter. We want to give the lowest number to the first substituent. So we could go ahead and name this molecule. If we use the numbering method on the left, this would be 2, 5, 5 trimethyl. What? We have 7 carbons, so that's heptane. 2,5,5-trimethylheptane, and the 2,5,5 beats 3,3,6 because the first number is lower. If there's a tie, then we want to give the second locant the lowest number possible. So if there's a tie at the first, we say, hey, do we have a second tiebreaker there? So on the left here, you can see that we've numbered the molecule from right to left, giving our first substituent would be at the 2nd carbon. So if we go over here on the right and compare, if we numbered from left to right, our first substituent is also at the 2nd carbon. But then on the left, on the molecule on the left, you can see that our second substituent is at the 3rd carbon. In the molecule on the right, our second substituent would be at the 5th carbon. So our substituents for the left molecule would be at 2, 3, and 6. Okay? The substituents numbering it according to the one on the right would be 2, 5, 6. So 2, 3, 6 beats 2, 5, 6. So we're going to number it as it is done on the left. So these are the same molecule, but it's just different ways of numbering. The one on the left is correct. So if we don't have a tiebreaker, as far as numbering, then we want to assign the lowest number according to the one that comes first alphabetically. So either of these, so notice that our carbon chain here, this is another thing that kind of trips students up sometimes. Notice our carbon chain is 5 carbons long. So if we number it on the left, 1, 2, 3, 4, 5, you can see that the chlorine and the bromine don't count in that numbering scheme. These bonds from the carbon 5 to the chlorine, carbon 1 to the bromine, those are bonds to the bromine and the chlorine. The carbons are the ones I'm drawing here with the dots. Okay, so keep that straight. This is a 5 carbon chain. And the substituents are chlorine and bromine. So the chlorine or the bromine, either one of those could be given carbon number 1, depending on which way you start numbering the molecule. On the right here, we have the same 5 carbon chain, and we have chlorine versus bromine that we could give as carbon number 1. So since B comes before C in the alphabet, we're going to use the way of numbering on the left because that's going to give bromine the lower number. So it just looks better to say 1 bromo 5 chloro than to say 1 chloro 5 5 bromo 1 chloro, right? So it would just look better to do it that way, and that's the correct way to do it. So the same rules apply for cycloalkanes. Okay, 113 is going to beat 133. So the left way of numbering this chain, 1, 2, 3, 4, 5, 6 would be correct because this would be 1, 1, 3 trimethyl cyclohexane. Okay, on the right we have 1, 3, 3, so that would be the incorrect way of naming it. So this molecule is 1, 1, 3 trimethyl cyclohexane. Alright, so that's the way we do it to assemble the name. So we find our parent. We identify, we assign a locant to the substituents, okay? Identify the substituents, assign them a locant, and assemble them alphabetically, okay? And then we put the substituents before the parent in alphabetical order. We assign a prefix di, tri, tetra, penta if we have multiple substituents, okay? And then we put the number in front of that. But notice that di or tri is ignored when alphabetizing these substituents. The only prefix that we consider is iso. So if you have isobutyl or isopropyl, you do use that I for alphabetization. So here's the summary of our naming rules. Identify the parent, identify and name the substituents, number the parent chain, assigning a locant to each substituent, and then list the numbered substituents before the parent name in alphabetical order. So let's go ahead and do some examples. Let's go ahead and work an example and try naming this molecule. So according to our rules, we're going to find the longest continuous carbon chain. In this case, the longest carbon chain is the 6-membered ring. So we have the 6-membered ring. Right along this blue path. Okay. And then we have 3 substituents, and I'm going to box those in. 1, 2, we have 4 substituents. We have 2 methyl groups on that carbon, numbered 4 here. And so let's go ahead and identify our substituents. At the top we have a tert-butyl group. Okay, next we have an ethyl group. Okay, and next we have 2 methyl groups. Now the interesting thing about this is that the author has given those 2 methyl groups the numbers at the carbon number 4. But if we want to correctly number this chain, the correct way to do it is actually not along that red path. The correct way to number the chain is going to be to number it giving our first substituent the lowest number. So we could do that either to the T-butyl group or to those two methyl groups. But then notice that our second substituent is going to have the second lowest number. Okay, so we have two different options here, our substituents being at 1, 2, 4, 4, our substituents being at, if we made this, if we follow the blue path, the two methyls are at carbon 1, 1, 1, and then 3, 4. So the author of this slide has actually numbered this parent chain incorrectly. Okay, our methyls are at carbon 1, the ethyl group is at carbon 3, and the tert-butyl group is at carbon 4. So in fact, we need to now alphabetize the substituents. Okay, and so the first one is going to be tert-butyl, because we don't look at the tert, we look at the B there for alphabetization. So that's going to be tert-butyl, which we only put the hyphen here because that's just part of the name. Okay, and then next we're going to have our ethyl. Okay, and next we have two methyl groups, so that's going to be a dimethyl. Okay, okay, and then our parent is cyclohexane, because it's the 6-carbon ring. Now, where I disagree with the author is the numbering. Okay, so we have 1, 1 dimethyl, 3 ethyl, 4 tert-butyl. Okay, and so we have to alphabetize that to put it all together. So it's going to be 4 tert-butyl, 3 ethyl, 1, 1 dimethyl, cyclohexane. Okay, so this slide was numbered incorrectly. So normally for my students, if they got those numbers out of whack on a test, I probably on a molecule like this wouldn't take off much, if anything, for that. Unfortunately, if you're doing it in Wiley Plus, it may deduct points, or it may just count the whole thing wrong. So you have to be very careful. So let's do a few more examples here. These are from problem set 4.8 in version 3 of Klein. Okay, so we want to find the longest continuous carbon chain for molecule A. Okay, and that's going to actually be this blue path. If I went this way, then I would end up following a shorter path, right? So the blue path is going to be the longest path. And we want to give our first substituent the lowest number. Okay, so that would be 1, 2, 3. If we go from left to right, or 1, 2, 3 if we go from right to left. So we've got to have a tiebreaker here. If we go along the blue path, our second substituent would be at carbon 4, 5, 6, 7, 8. If we go along the orange path, our second substituent would be at carbon 5. So we're going to follow the blue path. Okay, and so that is a derivative of octane because we have 8 carbons. We're following the blue path, so we have 3 methyl substituents at carbons 3, 4, and 6. So we have 3, 4, 6 trimethyl octane. Okay, the next one, B, we have our longest carbon chain is going to be the cyclohexane ring. We only have one substituent. It's connected here, so we can just call that carbon number 1 and number our ring around that way. It doesn't matter which way you go either because it's just one substituent. Now this is, the common name for this substituent is sec-butyl. Okay, but it's also a 1-methyl propyl. So if we start numbering at the carbon attached to the main chain, this is a propyl group, and we have a methyl group at the first carbon. So 1-methyl propyl in substituents, in parentheses, cyclohexane, and that 1-methyl propyl group is at the first carbon. So we could say 1-methyl propyl cyclohexane. That's why you have to put the parentheses there, because you're usually going to have a number out front. But since it's at the first carbon, we could just leave that 1 off because it's understood to be at the first carbon if you don't put the number there. So for example, substituents for the halogens, their prefixes like chloro, bromo, iodo, and so forth. So if I had a chlorine on this molecule, my carbon chain, I would start numbering it there. 1, 2, 3, 4, 5, 6. So this would be 1-chlorohexane. But since that's at the first carbon, the chlorine, I can just leave that 1 off, and we could call that chlorohexane, because it's understood, the substituent is understood to be at the first carbon if that number isn't given. Okay. All right, my next molecule, my longest path, is going to be along this blue path. 1, 2, 3, 4, 5, 6, 7. So it's going to be a derivative of heptane. If I go from left to right, that's going to give my substituents the lowest numbers possible. So 7 carbons is heptane, okay? And I have a methyl at carbon 2 and an ethyl at carbon 3. So I want to alphabetize those. That's 3-ethyl, okay? 2-methyl heptane. All right, next I'm going to do I, and so if we number this 1, 2, 3, 4, 5, 6, 7, I have a T-butyl group at carbon 4. If I go the other way from right to left, 1, 2, 3, 4, 5, 6, 7, it doesn't matter whether I go from left to right or right to left. In this case, my substituent is at carbon 4. My parent is heptane, okay, and that substituent is a tert-butyl. Heptane, okay, or I could call that, if I want to use complex naming, that is a 1,1-dimethyl ethyl group, okay. The next molecule, I have a derivative of cycloalkanes as my parent. And so it doesn't matter if I start numbering here or here. I could call either of those carbon 1, but I want to give the second one the lowest number. So let me go 1, 2, 3, 4, 5. So what I wouldn't do is 1, 2, 3, 4, 5, right? That would give me 1, 4 versus 1, 3. So I'm going to go along the orange path, okay? So at carbons 1 and 3, I have an isopropyl group. So that's 1, 3 isopropyl cyclopentane. All right, the next molecule, we may have to work a little bit to find this parent. So let's start numbering. 1, 2, 3, 4, 5. That's probably not it. 1, 2, 3, 4, 5, 6. That's probably not it. 1, 2, 3, 4, 5, 6, 7. I think that's going to be our longest carbon chain. Let's also try 1, 2, 3, 4, 5, 6, 7, 8. Whoops. We found an even longer carbon chain. So do I want to number as we have it there, or do I want to go from, say, 8 to 1? Do I want to go from this way, or do I want to go the other way? Okay, so I'm going to go along the yellow path because that's going to give my first substituent carbon number 2. Okay, so this is a derivative of octane. Okay, so we have 8 carbons. At carbon 2 we have a methyl. Carbon 3 is ethyl. Carbon 6 is methyl. So we have 2, 6 dimethyl, and then we have 3 ethyl. Ethyl comes before methyl, so that's 3 ethyl. 2, 6 dimethyl octane. Okay. All right, and the next thing we're going to do, the last in this presentation, is to go from a name to a structure. Okay, so we're going to do 2 examples of that. So for A, we have 3 isopropyl 2,4-dimethyl pentane. So pentane is a 5-carbon chain. Okay, like that. So so let's just number 1, 2, 3, 4, 5. At the 3rd carbon, I have an isopropyl group. Okay, so that's going to be like this. And at the 2nd and 4th carbon, I have methyl groups. So here's my molecule. Okay, for B, I have 4-ethyl 2-methyl hexane. So a 6-carbon chain is my parent. 1, 2, 3, 4, 5, 6. And at the 4th carbon, I have an ethyl group. At the 2nd carbon, I have a methyl group. So this would be my molecule. And again, I have the parts of the name of an organic molecule here for your reference. So we're going to use some of these other parts. So far we've discussed parent and substituents. Later on, we'll learn how to include unsaturation, functional group, and in the next chapter we're getting into stereochemistry. So we'll continue this discussion of chapter 4 of Klein Organic Chemistry in the next talk.